Hi everyone, this is Mo, and in this presentation I'm going to talk about enhancing security in Polkadot and Substrate by navigating Rust and blockchain vulnerabilities. So, so in this talk, basically, I introduce you, some basics in Rust, and then we navigate through a security model of Rust, and then in the second part, we talk more about blockchain vulnerabilities with the focus on the Substrate framework for the Polkadot ecosystem. Before we get started, briefly about me. My name is Mohammad Reza Ashuri, or you can call me Mo. I did my PhD in cybersecurity in 2020 from University of Potsdam. Then I did a postdoc in system security in 2021 at the University of Virginia Tech. Here, I regularly basically publish content regarding software security and cyber security, and mostly blockchain security, cloud security as well. And you can actually find this information, on my blog. You can follow me on YouTube channel. Sometimes I upload videos, technical videos or presentation like this. You can follow me on GitHub. I have like ideas and code, snippet code, and things like that there. Or you can basically get in touch with me on LinkedIn, or just drop me an email if you have any question or you have any ideas. So before we talk about security stuff, maybe it's good to know about Rust for those of you who are unfamiliar with the language. So Rust um, basically is a system programming language, and it was introduced to be a safer alternative to C and C++. In other words, we want to gain the same level of performance and basically having that kind of performance and control, and being able to write a wide range of applications from system drivers, operating system, endpoint APIs, blockchain apps, even web applications. So it's basically generic and general purpose language. Um, this language is statically typed, and that being said, that the type of variables and expressions need to be determined and checked during the compilation time. It's not at runtime. And it's basically, it aims to provide a memory safe basically build, and that's why it's also very popular among commercial projects and also blockchain project, because safety and lack of vulnerability is something very critical. So now let's talk about Rust security model. So briefly, Rust security model is geared toward the concept of ownership and type system. And ownership itself is something that's enforced by a core component which is called borrow checker. So borrow checker basically is a part of the compiler, and is responsible to basically check your source code during the compilation time, during the compilation process, and make sure there is no memory violation, so it's memory safe. So we don't want to have things and issues we have in C and C++. And it also want to make sure there is no data races. So if I want to give you an example, if you are, for example, familiar with Java, uh, borrow checker is very similar to garbage collector in Java, okay? But it's more efficient in a way that garbage collector actually functions during the runtime. So for example, when you have a Java code, you compile that and execute that, you have a Java process, okay? You have a process. And garbage collector actually act at runtime to clear up heap memory, and remove wasted memory, basically handling dangling pointers and things like that. Efficiency, memory efficiency, and basically removing wastes and so on. Because of that, because the garbage collector functions at runtime, it imposes basically down slowdowns basically to your performance. So your code is not as fast as um, like a normal binary without garbage collector. Okay. Whereas when you use a Rust build, a Rust binary, this borrow checker basically already guarantee this memory safety of your code, so it doesn't need to check stuff basically during the runtime. And by doing so, we have way more faster binary. So now let's actually have a look at the borrow checker in Rust and see how it works and what's the distinction between that and a language without borrow checker like C or C++. So here we have a C code. Maybe you can pause this video and think about it. What is there anything wrong here, or if it's something wrong, what would be the issue? You can think about it for a few minutes, before we continue, but I continue and address that. There is something wrong in this code. It's a simple snippet code. At line 6 here, we declare a pointer, and through the function str_dop, we allocate a part of memory with this literal string hello. We put it there, and we basically bring back the address to this pointer. So x here, this pointer, now point to this part of memory, which we hold the string hello. We just have memory allocation here. At line 7, the function free basically free the memory associated to the pointer x, which means that memory that is allocated for the string hello. So we deallocate that memory space. However, x still is valid in C or C++. Because of that, at line 8, we try to print the content of x, and here we actually encounter with undefined situation. We actually don't know what exactly happened. So here we might actually get memory violation error, memory corruption error, and something breakdown. We may actually mess around with with other processes in our operating system. It depends on the host machine and host operating system and compiler. We may also print some random values associated with the address that x is still pointing at, And even though that address is freed, still it can be used by garbage value. It could be, it may actually hold garbage value, or it may be used by other processes. It may also expose some credential information like private key and things like that from other processes or from our process. So the situation is really unknown, and this is basically undefined behavior that we have in C or C++. So if you try to compile this code in C or C++ compiler, any standard compiler right now, you probably don't see any warnings or any errors here. This code gets compiled and executed without any issues. And that's the main problem actually in C, because this is a simple snippet code. But imagine what you have when you have a huge, like operating system, when you have I don't know, some components for a car, or some factory line code, There are a lot of complexity, we have a lot of code, and we don't want to face unknown situation, right? Because the result could be deadly. And that's a huge problem here in C and C++. If we convert the same code, the same snippet code here into Rust, over here, for example, at line 2, we define x, and then we create a string object, we allocate some memory space, we assign that to x. At line 3, we drop x. What happened here when we drop x? We basically deallocate the space, and we take the ownership of x. From now on, x is invalid because it doesn't have ownership. And at line 4, we try to print the content of x, and here actually the borrow checker during the compilation time catch us and say, hey, x is not valid anymore, and so you cannot even compile the binary code. So we can't even make any binary here. So that's how it provides safety and security in terms of memory violations and memory safety. However, there are some caveats. If you write a code in C, it's not always memory safe. Why is like that? Because we can also use raw pointers, and also we can use unsafe blocks. So unsafe blocks, as you can see here, temporarily disable the borrow checker, and we can get over borrow checker. And in this case, this is the manipulated code, I made it out of this one. And if you try to compile this, it actually compiled, and basically it builds and creates, gives you a built binary Why is it like that? Because some developers use unsafe, and you might ask, okay, why people should use unsafe? There are different reasons. I'm going to talk about that because this Rust safety model actually imposes a lot of restrictions on your binary and your coding process. I will give you an example to basically clarify this point. The other reason is if you write like a large system, industrial system, or maybe low-level program like an operating system, a driver, something like that, you need to access certain memory addresses. You need to maybe interact with C or assembly code. You need to, and basically communicate with those stuff, those components. And in default safe Rust, you can't do that. And in those scenarios, you need to use unsafe blocks. So that being said, when you use some third-party library or create in Rust, you might actually have unsafe code, and those unsafe code can introduce the same memory issues that you can see them in C or C++ to your Rust code. So you got to be very careful about this. Indeed, a couple of years ago in 2020, I conducted a research regarding Rust fuzzing, Rust security, and I found a large number of open source third parties or libraries, we call them crate, for Rust, such as encryptions, network communications, and so on. Basically, they use unsafe blocks. They use a lot of unsafe blocks, which can be actually like a C code, so it could be also vulnerable to different issues. And they were vulnerable. Some of those they actually had vulnerabilities, and in this link here you can find the results. You can see the type of vulnerabilities I found. And the reason why is because developers also want to get in benchmarking and so on. They want to get the good, C, C++ or C++ basically performance and gain the same level of performance. So it's also like political reasons. But now let's talk about the limitation of raw security model. So there are actually from my perspective, there are two main limitations to this model. The first obvious issue is memory leaks. So memory leaks means the situation that we have wasted memory. We don't bring back that allocated memory properly to the system. This can be dangerous because if you have a lot of wasted memory, you create a lot of wasted memory and you don't manage them to remove them and bring them back, it slows down and sluggish your system. So if it's a blockchain system, then it could be dangerous for the network. It could actually bring down and slow down your nodes. Or if it's another distributed or any kind of system, financial system, any real-time system, it could be very deadly. The other problem is these wasted memories, they might also contain sensitive information about your credential, about admin pass, about specific addresses and things like that maybe enable hackers to exploit your system and do something basically malicious. And why is like that? Because memory leaks from the Rust security model doesn't lead to an undefined situation. Yeah, it might actually make problems, but it doesn't go to memory violation directly. And because of that, Rust security model just, ignore it. And there are actually interesting debates about that. I would recommend you take a look at this link here, and you can find more about this. The other basically limitation to the Rust security model is the complexity. So as I give you one example in the next slide, the complexity imposed by this security model, sometimes it could be quite confusing, and it may also block the compilation of your safe code. Even if you have a memory safe code, sometimes Rust and the borrow checker doesn't allow it to get compiled, and it's annoying, especially when you have larger scale code. Regarding complexity, have a look at this code here. We can pause this video and think about this, whether it's a safe, memory safe code or it's not. But I can interpret that for you. So this is actually a memory safe code. At line 2, we define a mutable vector with 3 elements. We initialize it with 3 elements. At line 3, we define an iterator. It is mutable. And through the method, the iter, basically uh, we iter basically we iter over the v elements without giving the ownership. And then at line 4 we just advance to the next block. At line 5 we try to replace the element on the slot 2, which is 5 here, with 3. And here the borrow checker actually catch us and stop us from the rest of the compilation. And even though this code doesn't do any harm to memory and everything is safe logically, uh, here the borrow checker stop us because it says that immutable borrow occurs at line 3. And here we can, for example, drop a v, or we can drop basically the iterator, or put the code in different scope to get around that. But still, it would be a lot of complexity for a memory safe code. So here, I would say by mistake, Rust, more specifically the borrow checker, stop us from the compilation of the code. If you have the same conversion of this code in C or C++, like C++ example here, and you can compile that without any issues and any problems. So here shows the pros and cons of using Rust comparing to C or C++. This link here also is very interesting. We can actually read about more details about the behavior considered undefined in Rust. All right, apart from that, I mean, from the security standpoint, as a security editor, the borrow checker is not everything. There is some kind of misconception between developers that they think if they use Rust code, the code is safe because the language is safe. So this is wrong. Especially this is common among developers who are unfamiliar with security concepts, or junior developers. Like I said, we might have memory leaks that Rust doesn't care about that. We might have logical issues. For example, if you design a staking program, design a token allocation program as part of your blockchain app, or basically voting system and a consensus, an algorithm for your consensus. If you have logical issues, basically this borrow checker doesn't really catch them because it's not looking for those kind of issues. It's just look for memory safety issues. That includes also lack of data verification and sanitization. It could be wrong security policies and so on. So in order to make sure your code is generally secure in different aspects, you definitely need to have some sort of defensive programming, which means when you design a function, you need to have unit tests for that. You need to check minimum with expected and unexpected value and make sure that function operates properly. This is also important if you want, for example, if you have a blockchain app and you want to outsource that for a audit company or freelance editor, because if your code doesn't have unit test, most of the credible companies or freelancers do not accept your code because it's just pre-audit state. Unit testing also enhances the readability of your code. It also is like a documentation for that. More advanced testing includes fast testing, such as symbolic or concolic or hybrid testing. I published actually a couple of papers in this regard, and also you can find in my YouTube videos and talks. Fuzzing is basically like unit testing on a steroid, I would say. In unit testing, you have just limited input. You introduce limited arguments and input to your function. Whereas in fuzz testing, we do it a wide range of basically input, various unexpected input. And the goal here is to crash and smash a function. So if a unit as a fuzz test basically can crash a function, that means that function is not safe and you need to fix the problem with that. And of course, on top of all of them, you need to have manual code review because you might have logical issues, you might have more sophisticated situation that fast testing or unit testing cannot catch them. And you need some expert to analyze, to interpret your code logic and the entire system. For example, the way the front end, work with the back end, with the blockchain layer, and so on, to understand and catch security problems. There are actually numerous tools for the Rust ecosystem that you can use to enhance your code security and performance. Here are three of them. Uh, they are very straightforward terminal-based tools, and you can basically put them to your CI/CD pipeline in order to enhance your production code. The first one is Cargo Audit. So this tool actually scans the cargo log file of your Rust project. In this file, you can find information about crates and versioning and so on of your project. And it also takes advantage of RustSec advisory database, which you can find basically publicly reported vulnerabilities for the crates, for the third-party libraries. And if this tool find any malicious, outdated, problematic crate in your code, basically it reports you. The other tool is called Clippy. This tool is more like a linter, but it also provides some security patterns, and it also scans for some security patterns like insecure random number generators. And it's overall good for your code quality. And the last tool is called Cargo Geiger. And this tool is very useful if you want to find if any of your third party or any of the crates contains unsafe code blocks, because if they contain unsafe code blocks, your code might be vulnerable to memory safety issues. So you need to be more careful. And Cargo Geiger actually check those stuff, and if it finds any unsafe code, it reports you. All right. Now let's talk about Substrate. What is Substrate? So Substrate is a Rust-based open source framework that was introduced by Parity. And this tool allows you to actually create blockchain for the Polkadot ecosystem very fast and with using a lot of reusable packages and code. So it allows you to create blockchain. It could be a standalone network or be part of Polkadot network as a parachain. It allows you to make palettes. So if you're familiar with object-oriented programming, palettes are like black box, like classes and objects you have. Classes with certain functionality, and you can use these classes in different projects, right? So it's same thing like that. It's a modular components that encapsulates specific functionality within the framework. So developers, for example, can use different palettes. They can also create their own palettes and create blockchain projects quickly. So these palettes there are a lot of off-the-shelf palettes. You can find them on the website. For example, for authentication, for staking, for governance, voting, and so many different basic operations. You can use the palettes and assemble and create your own chain fast. You can also create smart contracts, even though it's not the main functionality of Substrate, because it's more focused on the fundamental stuff, fundamental aspects of blockchain development. But through some palettes like the frame contract palette, you can also create smart contracts. Now let's talk about some common vulnerabilities in this ecosystem. But some of these, issues actually you can find them also in Ethereum, in the EVM ecosystem, or Solana and other ecosystems as well, right? But here the focus is on the Substrate framework and Polkadot ecosystem. So the first one is called insecure randomness. So randomness is a core part of many projects, Web 2 projects, Web 3 projects. We always need some sort of randomization or pseudo randomization for predictions, for lottery, for voting, choosing nodes based on random numbers, and creating, for example, random password and things like that. So randomness is important in software engineering and software security in general, not just blockchain. But in terms of blockchain, it become more serious and dangerous because we deal with assets and and those financial assets can get hacked, for example, and be stolen very fast. Uh, how we have this kind of issue like insecure randomness if you use like weak or predictable randomness sources. This kind of randomness sources can be potentially anticipated or manipulated by malicious actors. So, for example, in the substrate ecosystem, we have a palette called randomness collective Philip palette. And this is basically a vulnerable palette because the randomness here is influenced directly by the past block hashes, which could be basically manipulated or anticipated because it take a look at the previous 81 blocks to generate a random value. So, in some sort of environments, malicious actors can actually impact about the previous blocks, hashes, or read them and guess the next random number. What would be the mitigation here? We can use a safe one like VRF or verifiable random function, and you can actually find this in the palette babe in the substrate ecosystem. The other problem, which is very interesting, is storage exhaustion. So this issue, as its name basically stands, it comes when some malicious actors, attackers can waste a lot of storage in our chain, in our code, in our system, in order to make it sluggish and basically unfunctional. It's some sort of DOS issue, right? So why it happens and when it happens when basically you don't have proper charging mechanism for using storage. For example, it's super cheap, or certain user can use a big chunk of memory, with cheap price, but there is no any limit on that. So it can actually cause bloating, storage bloating, and it cause some sort of DOS and make the system unfunctional. So in order to make sure about that, you need to have more algorithmic, you need to have better algorithm, better logic here. For example, you need to prohibit certain user to overuse storage. You can enhance your storage cost, by limits and so on. The other one is unsafe arithmetic. Unsafe arithmetic happens when you basically have some arithmetic operations like, let's say, token assignment, staking, calculation, um, treasury, accounting, or balancing and things like that. For example, in blockchain ecosystem or even non-blockchain ecosystem, and it happened, for example, when wrapping, around numbers. So if you write a code in Rust and you write this in the debug mode, if you have any arithmetic overflow and underflow, basically your binary crashes, it panics and crashes. But the problem here is if you compile the code in the release mode, for example, for production, the Rust compiler actually here ignore this issue and try to wrap around that arithmetic value, around the overflow or underflow. So here it doesn't panic, so we don't notice the issue. On the other hand, it gives us wrong numbers, and that could be critical and big problem because, for example, hackers can um, steal a lot of tokens or access to unauthorized assets. And mitigation would be using safe functions like checked underline add or checked underline sub for arithmetic errors. So we have unsafe conversion similar to arithmetic errors. It happens mostly when we have downcasting. We have like a numerical type and we try to convert this type to another one without proper checks. And sometimes it can lead to overflow or incorrect, inaccurate values, and attackers can actually take advantage of that, like the previous one. So we need to have proper algorithm here. We need to avoid downcasting and use safe conversion methods like unique underline saturated underline into in our code, substrate code. Reply issues are quite interesting. I've also seen them in other projects in like Cosmos SDK and any other blockchain. This is quite interesting issue. It's mostly core level issue. And this vulnerability arises from improper handling of transaction nonces. So that being said, this allows attackers to use or repeat the same transaction over and over again. So they can make it like 1,000 times in order to take down a node. So it overwhelms a node with the same transaction. This happens when in your code you don't check for, you allow basically a transaction to get processed without proper limitation or any control or anything like that. It can also happen like in IBC or um, you know XCM, ecosystem in IBCs, I mean general, any uh, um, um, any communication between different chains, and that can be actually very dangerous if you just accept transaction coming from a user or from another chain without adding some sort of limit. So in order to make sure that doesn't happen, you need to have a proper mechanism, proper logic in place to do not accept transaction repetition. So it's very important, and you need to have some sort of logical functionality for that, some proper logic basically implemented to handle this. And lastly, we have outdated crates. It's rather simple, but it's very common in industrial code, especially for blockchain code when you use different dependencies and framework. Uh, this file here, as you can see, it's a crate for a Substrate blockchain project. This is basically cargo lock of that, and as you can see here, developer here used various version of Substrate, and that actually cause inconsistency in your code, and it actually may introduce different vulnerabilities. I mean, first of all, your code is complex, is inconsistent. It might have different vulnerabilities because of the using previous version of, for example, Substrate. And this is also a common problem among blockchain and non-blockchain developers, especially when your code comprises a large number of external dependencies or crates. So how to mitigate that? You can use the newest and safest version of dependencies, ensuring about the consistent versioning across all your crates. So that was it. I hope you enjoyed this talk. If you like this sort of content, and if you like to know more about the details, about different vulnerabilities, the snippet code, and more sophisticated things, more security stuff, you can follow me. You can follow my blog, YouTube, GitHub, LinkedIn, and you can contact me via email. Thank you very much for your time.